Lattice energy. The strength of an ionic crystal lattice is reflected in its lattice energy. The lattice energy is the difference in energy between the ions packed together in a solid and the ions widely separated as a gas. It is always a positive number. It is strongly related to the electrical interactions of the ions which hold the solid together. Coulomb's law tells us that the electric potential energy of two charged ions, here Q1 and Q2, is proportional to their charges and inversely proportional to their separation, as is reflected in the below diagram. This is the source of the lattice energy of an ionic solid. Here's the magnitude of the two charges, here's Coulomb's constant, and here's the distance between the two charges. Comparing the lattice energies of these ionic compounds is illustrated by Coulomb's law. The greater the magnitudes of the two charges, the greater the magnitude of the lattice energy. So here for sodium fluoride, the charges are +1 and -1. Magnesium oxide, twice the charges, and it has a greater lattice energy. The smaller the atomic radii, the greater the magnitude of the lattice energy. All right, so here's our atomic radii for fluorine, for chlorine. So the lattice energy is going to be bigger with the ionic radius of fluorine. And you can see 923 kilojoules per mole versus 786 kilojoules per mole. Melting temperature is the temperature at which an ionic solid loses its crystal lattice structure and enters the liquid phase. Ionic solids with a higher lattice energy have higher melting temperatures because more energy is needed to break the electrostatic interactions between the ions and release them from the solid and get them moving. Due to Coulombic forces, the melting temperature increases as the magnitude of the charges of the ions increases and/or the ionic radii decrease. Note, while ionic solids cannot conduct electricity, molten ionic compounds do conduct electricity. The electric current is due to the movement of charged ions rather than the flow of electrons. And here's the energy that was put into the system to break the ionic bonds. As lattice energy increases, the solubility in polar solvents decreases as it's harder for the water molecules to pull apart the ionic solid and separate the various ions from each other. We can make predictions about the boiling points of molten ionic compounds since ionic bonds are broken more easily as their lattice energy decreases. Which will boil at a lower temperature? Lithium fluoride or beryllium oxide? Why? Answer will be on the next slide. The magnitude of the charges on both lithium and fluoride are 1, so their product is 1. The magnitude of the charges on both beryllium and oxygen are 2, so their product is 4. Lithium fluoride will boil at a lower temperature than beryllium oxide since lithium fluoride has a lower lattice energy. Lithium chloride will boil at a higher temperature than sodium chloride. Why? The sodium ion has a larger radius than the lithium ion, so the distance between the centers of sodium and chlorine in NaCl will be greater than that between lithium and chlorine in lithium chloride. That results in a greater electrostatic attraction and a greater lattice energy in the lithium chloride than the sodium chloride. Right, they're closer together. The lithium is closer to chlorine than the sodium is to chlorine. So sodium chloride will boil at a lower temperature than lithium chloride since sodium chloride has a smaller lattice energy. Which of the following ionic compounds would have the lower melting temperature, potassium chloride or sodium chloride? The potassium ion has a larger radius than the sodium ion, so the distance between the centers in potassium chloride will be greater than that between sodium and chloride in sodium chloride. That results in a greater electrostatic attraction and a greater lattice energy in sodium chloride than potassium chloride. So potassium chloride will melt at a lower temperature than sodium chloride since it has a smaller lattice energy. Given the information in the table below, rank the following ionic compounds from greatest to least lattice energy: magnesium oxide, sodium chloride, and sodium fluoride. The magnitude of the charges on both the sodium ion and the chlorine ion are 1, so their product is 1. The magnitude of the charges on the magnesium ion and the oxygen ion are 2, so their product is 4. So let's just write a 2 here, and we'll go a 4 here. Sodium fluoride has a lower lattice energy than magnesium oxide because sodium fluoride has a lower boiling point and a greater magnitude of the product of its charges. Now let's finish it up here. Sodium chloride will have a lower lattice energy than sodium fluoride. Why? Because the R is greater for sodium chloride, right? Chlorine, the chlorine ion has 181 atomic radius, and fluorine is 133 picometers. So, ranking from greatest to least lattice energy, we get magnesium oxide, sodium fluoride, and finally sodium chloride.